So today's Halloween day, so everyone can pick a bag for candy. Just pick one. Thank you. Thank you so much.
Thank you.
Thank you so much. I just created a new submission for the proposal. So proposal is due next Tuesday before the class, and I will post the problem set for today, later sometime today. So last time we finished talking about ADM algorithm, and this time we are talking about another first order method, but this is not for solving primal dual problem. It's for primarily. Oh, this is also useful for solving primal dual. Later I will show you a way to solve primal dual problem, the saddle point problem, purely from the primal perspective. But this will be the main technique we are talking about. It's mainly for primal. So the motivation is for non-smooth optimization. Remember, in convex non-smooth optimization, we learned subgradient method, for example. For example, for subgradient method, the complexity bound to find an epsilon solution in terms of function value is big O of m square d0 square over epsilon square. So, Halloween day, yeah, take a bag of candy. M here is the Lipschitz constant, Lipschitz continuity for the function f. D0 means the distance from x0 to the solution set. Epsilon is the accuracy that we are looking for. This is also optimal because this matches the lower bound for convex non-smooth optimization. Well, in many cases, the performance of subgradient method or some other method is somehow faster than this rate because this is too slow in terms of epsilon. If epsilon is 10 to the minus 6, then this is basically saying that complexity, the number of iterations to obtain this accurate solution, ignoring M and D, this is on the order of 10 to the 12. This is too large. Well, in practice, we usually do not observe such performance. That is because in many cases, the problem we are solving is structured. It's not like this one. This is for the black box model. Basically, you assume no structure in the problem. You just know it's Lipschitz continuity and it's convex. That's all the information you know. But in many cases, the problem do have some structure. Well, it is just that the algorithm does not take advantage of that structure, right? So Nesterov proposed this smoothing technique around 2005. This is basically to do a smooth approximation to the non-smooth problem. First, we apply a certain approximation, smooth approximation to the non-smooth problem. And then we apply the fastest algorithm we know for solving convex smooth problem, which is Nesterov acceleration, to solve this approximation problem. After that, then we have a convergence rate or complexity to this smooth auxiliary problem. And then you also need to take account for the approximation error between smooth and non-smooth terms. Okay, that's the basic idea. And in the end, we can improve this complexity just in terms of epsilon. This will be on the order of 1 over epsilon. This is the complexity as the case we apply, for example, proximal gradient method to smooth optimization. right? So you can see an improvement in terms of the dependence of epsilon. So let's consider the following problem. Consider this composite structure where we have three components, f, h, and theta. F and h are like what we considered before. F is closed convex, differentiable everywhere, and it's also L smooth. H is closed convex, and we know the proximal mapping for H, so we call it simple. We have an additional term, theta, which is the troublesome term. This is like the non-smooth part. Theta is convex, but this is not necessarily smooth. It can be non-smooth. And we do not assume proximal mapping for theta is available to us. So if we have no theta, you can apply your favorite algorithm, for example, proximal gradient or Nesterov acceleration to solve this. Basically, it's a smooth problem. Because for H, we know the proximal mapping, right? We do not need to worry about H, and we do not need to smoothify it. But for theta, this is one. It is both non-smooth and also not simple. So we need to smoothify theta to apply this smoothing idea.
Do we assume that theta is closed?
Yes, yeah,
Oh,
I
okay.
just ignore it here.
Thanks.
So we call a function theta to be C1, C2 smoothable. There exists a positive scalar mu and a convex function, differentiable function theta sub mu, such that the following two conditions hold. First, theta of x is sandwiched between theta mu x and theta mu x plus C2 mu for any x. So it has a lower approximation theta mu. This is going to be the smooth approximation, and it's not far away from theta mu from a ball. It's bounded by C2 times mu, and because this is a smooth function, so we also assume the gradient to be Lipschitz continuous, and this is going to be the Lipschitz constant C1 over mu. Okay, so in the algorithm, we are going to keep fx and hx as is. Well, we just smoothify theta. We use theta mu to replace theta, and then consider the corresponding auxiliary problem. So we consider this auxiliary problem. So in this auxiliary problem, f of x is convex smooth, theta mu is also convex smooth, and h is the one we have approximate mapping. So we can combine all the smooth terms together. We call the sum of the two as f mu of x. And this function is, of course, convex, different from everywhere, and the gradient is this much Lipschitz continuous because the f component is L Lipschitz continuous. Theta mu is C1 over mu Lipschitz continuous, and the sum of the continuity constant of the two is just the sum of the two continuity constants. It's upper bounded by this one. And now we can apply, for example, Nesterov's one of the Nesterov acceleration methods to solve this problem. And for example, we are going to use the Fista variant. Recall we talked about three update schemes, right? We had a framework for Nesterov's acceleration, and we mentioned the three updates. for the pair y and x, right? One of them is Fista. The other two, we have three rules. One is Fista. The second one is AT, plus one is LLM. So we are going to use Fista because in practice, this one takes two proximate mapping of H. This one takes one, this takes one. And in practice, people do observe this one is usually faster than the second rule. This is the same algorithm as we presented before, except that now we assume the function f, and so we assume the function f mu is differentiable everywhere. Before we assume it's only differentiable on the set omega, and so we need to do a projection of this point onto omega. But here it's just a projection onto Rn, so that means basically we do no operation here. Right? So actually it's just this is actually extrapolation, right? Because this constant minus ak over little ak is just 1, so this is actually an extrapolation, and this is a interpolation. It's a combination of the 2 points. Another difference is previously we do not specify how large this constant is, we can do either a constant step size or line search. But here we just take the constant step size. The step size is 1 over L mu, and here the constant is just the L mu. We do not do any adaptive approach here. The most computational expensive step is this one. Is to basically this is to approximate mapping of H of a certain point. Okay, and here this is a linearization of the smooth function f mu. In the original algorithm, here it's just a f because we have no zeta component. Okay. And the convergence of this algorithm is shown for the yk plus 1, yk sequence. You will show 5 yk minus 5 star converges to 0 on the order of 1 over k squared. Similar is basically saying if you choose mu to be this small and then apply this algorithm onto the auxiliary problem, then you will find an epsilon solution yk in this many iterations. This is, if you ignore this part, like C1, C2, either of them to be 0, then this complexity is exactly the Fista complexity for solving the smooth optimization f plus h. This error is for the approximation error, right? Because we're solving this approximation problem, so there is a difference between zeta mu and zeta. This part carries the approximation error. Other than that, you have this accelerated complexity, right? It's square root of 1 over epsilon. The proof is very simple. We basically just need to apply the Fisa algorithm to obtain this complexity, and then calculate how much the two functions are different. And then, because of this choice of mu, we will automatically have this approximation error, the complexity for the approximation part. The starting point of the algorithm, the analysis is this observation. Recall that for the zeta function, we call it C1, C2 smoothable when zeta of x is sandwiched by zeta mu and zeta mu plus a constant, right? Initially, we have this inequality that is for the, this is the definition of theta to be C1, C2 smoothable. And then we just add f and h of x to each of the terms here. Then we have this standard deviation inequality for phi and phi mu. Okay, and then let's directly bound this term. So we first subtract and add and subtract two terms, phi mu of yk and phi mu of x star. X star is the minimizer for phi. Here, phi star means phi of x star. This x star is the minimizer for the original problem, not for the auxiliary problem. Okay, so this is an identity, and then we try to bound, upper bound each of the difference terms here. The first one is upper bounded by a constant C2 times mu because of this inequality, right? We just use the second part, take x to be yk. And for the last part, this phi mu is underneath phi because of this inequality, right? Because of the first one. So we have first one and last one both bounded by using the observation there. And this one here, because we are interested in the optimality gap for the phi mu function obtained by using FISA algorithm, right? And so we need to turn this one to be the real minimizer for the phi mu function. And it's just because this is the minimizer, so this gap is upper bounding this gap here, right? Because you are minimizing, so this quantity minimum of phi mu is smaller than phi mu of any point. So this is a larger bound. And this bound can be obtained using the FISTA algorithm, right? We just apply FISTA and using the convergence rate we had a few lectures ago for solving the convex smooth optimization. Just apply it to this new function, phi mu. Let's call the arc-mean of this new function phi mu to be x tilde star. And the convergence rate we had before is that for any function, suppose the function is phi mu. For function phi mu, the optimality gap obtained by FISTA is this much. It's 2 2 times the Lipschitz constant for the gradient of this function, and the distance between 0 and the minimizer, take the norm square, divided by k to the k square. Okay, this is some result we had before. And now let's plug in the value for mu. Here we specifically take mu to be epsilon over 2 over C2. So this is just epsilon over 2 plus the same bound here. We can also make it explicit, because here L mu, we take it to be L plus C1 over mu. L is the smoothness for F, C1 over mu is the smoothness for the smooth approximation, the function zeta mu. This point should be x to the star. Should be the minimizer for the phi mu function. Okay, so let's continue here. Our goal is to find an epsilon solution. So we want to upper bound the whole thing here at epsilon. So that is to say, we want to bound this term by epsilon over 2, right? So our goal is to bound 2 times from this inequality, we can derive the order of k. K is on this order. Okay, and because we know mu is epsilon over 2c, 2 over epsilon over 2c2. So let's plug in the value for mu. Then we have an explicit bound. And here, from here to here, we just apply a simple inequality. Square root of a plus b, a and b are 2 positive scalars. This is upper bounded by square root of a plus square root of b. Right, then we can separate the 2 terms. This is upper bounded by square root of L plus square root of C1, C2 over epsilon. Right, and then we put this epsilon inside. Then we have square root of L over square root of epsilon and this term. So we have square root of epsilon, square root of epsilon. So in the end, we have epsilon here for C1, C2 term. Because we are, the discussion is about the order, right? So this inequality becomes equal to, because we are in an order. Right? This here it means the bound here. Okay. Okay, so this complexity really shows that if you apply the smoothing technique and then use Vista algorithm, you can really improve the complexity from 1 over epsilon square to 1 over epsilon, right? C1, suppose C1, C2 are not too big, then this is on the order of epsilon. It's an improvement because you know some structure of the function. You know the function zeta is smoothable. That is something we do not assume if you apply the black box model. Let's do an example, and this is really a set point problem. We are minimizing over x and maximizing over y. Here, the function has this bilinear structure. So the part that connects prime and do x and y is this inner product term ax and y. This is linear in, if you fix y, this is linear in x. If you fix x, this is linear in y. So this is called a bilinear term. The setup is pretty much like what we usually have. F is the smooth function. It's closed convex, differentiable everywhere, and it's L smooth. H is a closed convex function, and simple means that we have the proximal mapping. And for G, this is the difficult function. It's for the do part. It's closed convex, and we do not assume smoothness for H and no strong convexity. We just know it's closed convex. And we also assume domain of G is bounded. This is for some technical issue. You will see why we need boundedness later on. You can apply many algorithms we mentioned before, either the Chambly-Poke, an instance of the insect proximal point framework, or using the ADMM to solve this problem, using both prime and do, right? Keep primal updates and then the do updates using augmented Lagrangian. Or you can first turn this problem, this primal do problem, into a primal one, and then solve the primal one directly. And we are going to use the idea of smoothing to solve this in a primal perspective. So then we need to do a reformulation of the problem. Right. The way we reformulate is very simple. We just take all the primal parts to be in front of the max. So we just put everything in terms of y together and put max over it, and then take all the primal information in front of the do information. Right. From here, it's easy to see this is actually in the form of a conjugate function. Recall for function f is conjugate f star. Usually we use sup, but here I'm just using max, assume the supremum is obtainable. And this is right. Suppose this is the definition of conjugate function, right? And here this is actually in terms of the conjugate function, view this ax as a new vector, right? So then this part, the max part, actually g star of ax right. Now everything is in terms of x, right? These two are like what we considered initially, right? We have a smooth function and a simple function that has prox mapping, and the other part we know it's convex, but it may be very difficult to solve the prox mapping. But we do know this function is convex in x because this is a conjugate function. Conjugate is always convex, no matter this function is convex or not. But we just don't know if it's smooth or strongly convex. This is the idea, just to make use of this max structure and use the definition of conjugate function, then turn everything into primal variable x. Yeah, so this is going to be our function set of x. But then we know set of x is convex. Let's now consider another function called g tilde. G tilde is a closed and mu strongly convex function. So g here is just a convex function, but here we are talking about another function that is mu strongly convex, g tilde. And then let's consider the conjugate function of g tilde. So this is the definition of conjugate function, right? So this is g tilde, the conjugate of g tilde of z. Let's call this function to be theta tilde of z. Then this theta tilde is convex because it's conjugate function, so it's always convex. And it's also differentiable everywhere, it's smooth. This is because g tilde is not only convex, but also strongly convex. Recall that we had a corollary in the lecture about mirror descent. We say that when this function is strongly convex, then the conjugate is smooth. And the modulus for the smoothness is exactly the inverse of the modulus for the strong convexity. So this is basically what the lemma is saying. This function, the conjugate function of g tilde, is convex differentiable everywhere it's smooth. And also the smoothness of the function, theta tilde, is just 1 over mu. Mu is the strong convexity. Right? This is a lemma the corollary we mentioned in the lecture about mirror descent. And also, we know what the gradient is. The gradient theta tilde is the maximizer for this supremum, for this optimization problem. And this is unique because theta tilde is strongly convex. So this can be viewed as a minimization of a strongly convex function or maximization over a strongly concave function, right? So the minimizer, so this is just gradient, not a subdifferential set. If this is just convex, then we have a subdifferential set. The subdifferential set for theta tilde is the same as the solution set for this problem. But now, because this is unique, this is strongly convex, so the solution is unique, then the first order information is also unique, so we have a gradient instead of a subdifferential set. Okay?
What is the gradient? Is g of z or y of z?
It's y of z. This means because here we are solving a maximization problem in terms of y, right? For fixed z, you have a y. So y is a function of z. This just means the maximizer for this problem, and it depends on z, right? Because z is an argument here. In our setup, we choose the function g tilde of y to be g of y plus a quadratic term, this parameter mu over 2. Here, this y0 is arbitrary. You just choose any point in the domain. This is just to convexify the function. Right? By adding a strongly convex term, this function becomes mu strongly convex, so that we can use this lemma to obtain a smooth approximation. Then Then let's use this conjugate function here, and we call this function to be theta tilde mu, because so this theta tilde mu is the same as this theta tilde. We just make it explicit about the dependence on mu, and the gradient of this function is also the maximizer of this one. We also put mu here to denote this depends on mu. And this is one over mu Lipschitz continuous. Let's take this z to be a times x and call this function to be theta mu of x. This is going to be the smooth approximation we are looking for. Right? This function is also smooth, but we just change the variable from z to x because we have a bilinear structure a times x in the product with y. Okay, and this function, you can check this is 2 norm of a square over mu strongly smooth. Right, when you take the gradient, a will come out, right? And then if you do the check the definition of Lipschitz continuity, you will have this a norm square, and this mu comes from here. Okay, so this is left for you to check, and. So from here we know this function is this much smooth, and recall that the function is C1, C2 smoothable. When one of the conditions saying that the function, so this is for theta, one of the conditions for gradient of theta mu is C1 over mu. It's just continuous, right? And now comparing the two constants, we know C1 is actually the norm of a square, right? And another condition is about C2. For C2, so we just need to compute theta x minus theta mu of x, calculate the upper bound, and divided by mu, we will obtain C2. In our case, theta is this function. Theta mu is the soup of this function, right? So then the difference between, actually this z is ax, right? We take z to be ax. So then the difference between the two, theta of x minus theta mu of x, this will be upper bounded by mu over 2. It's just the difference is just this term, right? So it's upper bounded by the maximum of that term. Here should be domain of G. Because the difference of the two functions is just a quadratic term. So this bound is the bound of the term, the difference is, of course, the constant mu over 2 times the maximum, right? This is an obvious upper bound. And this maximum between any 2 points, because y0 is also in the domain of G, y is also in the domain of G. So this upper bound is actually the diameter, right? Diameter of the set. Because we assumed the domain of G is bounded, so this is finite. Let's just call it mu d square over 2. And now we figure out what C2 is. Right, so we can take C2 to be diameter square over 2. Okay? Basically, this finishes the discussion about the set point problem, because we define what the zeta function is, and we also obtain its C1, C2 approximation, right? This is a smooth approximation. The smoothness is this much, C1 over mu. So we figure out what C1 is, and we also have this sandwich inequality. And from here, we also know what C2 is. And then plug in C1, C2, we will have the final complexity. So the complexity, we call the complexity is x0 minus x star to the here this L means the smoothness for F, right? So this is L smooth, and C1 so the complexity becomes big O this LXX means, because we are originally solving this saddle point problem, so this means it's like the second derivative with respect to the x. So this is for the Hessian, right? This is like an upper bound for the Hessian with respect to x, the L2 norm for Hessian, and which is the smooth parameter for the function f. This is the same complexity in terms of epsilon. This is the same complexity as if we are solving the original saddle point problem, because we do not do acceleration for the original problem. We just have 1 over epsilon complexity. Okay, so this finishes the discussion on the smoothing technique. In the last few minutes, let me present another variant of Fista method. So what's important, one more observation for the smoothing techniques. What's important is not only the smoothing technique, but this idea of using the lemma we presented here. So assuming that you originally have this function originally we have this function, let's call it gx. Gx is the g of y. G of y is a convex function, right? But we don't know whether it's smooth or not. The key idea in this example is to try to convexify this function so that the conjugate function will be smooth, right? That's the main idea. Consider this function instead of fx, then the function g tilde will be smooth. This idea has been used in many places. Smoothing is one of the places where you can use it explicitly for the saddle point problem whenever you have this max structure. So this idea is quite important to strong convexify a convex function so that the conjugate will be smooth. This is a way to construct a smooth function. But this idea is quite important in terms of algorithm design. Let me present you another way of stating the FISA method. To be consistent, let's also do it in terms in this smoothing setting. Let's consider we have both f(x) and the smooth approximation set a mu function. Let's call the input to be x tilde 0. In this alternative presentation, we only maintain two sequences of iterates, yk and x to the k. We eliminate the xk sequence. Recall that previously we had three sequences, right? Yk, xx to the k, but now we just have two sequences. This is just some simple algebra. And another thing to simplify is about the scalar sequences. Previously we had two sequences, little ak and capital AK, and now we only maintain this tk sequence. So you can check this algorithm is the same as what we had previously by showing these two lemmas. First, we show that this x to the k, so this is the definition we had previously. So this x to the k is exactly this x to the k, a Combs combination of yk and xk. And xk is obtained in this manner. This is how exactly we obtain the xk sequence. And also for the tk, this is connection between tk and the previous sequences, little ak and capital AK. It's the ratio between ak plus 1 and little ak, which is also equal to ak times L mu. L mu is this sum of smooth parameters. And also tk satisfies this quadratic equation. By solving this quadratic equation in terms of tk plus 1, you can actually show tk plus 1 is exactly this one here. Right? View this as a function equation in terms of tk plus 1. Right? This is 1 plus square root of 1 plus 4 tk square over 2. Right? So by showing these two lemmas, you can show this presentation is exactly the same as what we had before. But it simplifies a lot because you only maintain two iterate sequences, y and x tilde instead of three. We ignore the x. And also for the scalar, you just maintain one sequence, tk, instead of two sequences, ak and ak plus 1. Another observation is that this tk is also the step size. So step size is the same as the step size rule 1 in Frank-Wolf. Recall that Frank-Wolf is a projection-free method, right? Because all the methods we talk about today needs to do a proxy mapping of H. In Frank-Wolf method, you do not need to do proxy mapping of H, but you need to minimize H you need to minimize the linear approximation plus H instead of quadratic approximation plus H, so that you can avoid the proxy mapping of H. Or if H is an indicator of a convex set, this is projection-free because you do not need to project onto that set, but you minimize the linear function over the set, right? And sometimes it can be simply done by solving a linear programming. So tk, remember that we had three subset rules. This is the predefined subset rule. We had two others. One is an exact minimization, the other is an adaptive rule. This is the same as the first subset rule for Frank-Wolf. And it is this one, so it's in Frank-Wolf we choose this one to be 2 over k over 2. And for this, recall that for this subset rule to interpret it, we use acceleration as example. We connect this tk we connect it with the step size in acceleration method exactly through this relation. So this step size is not a magic. It's also, this tk is also used in Frank-Wolf and also is used in FISTA and other acceleration schemes. Okay, I think we can stop here, and I will post the problem set for later sometime today, and it will be due on November 16th before class. TK actually, TK is the inverse of this one. TK is TK is k plus TK is greater than or equal to k over 2 divided by 2, and in Frank-Wolf is taken to be equal to this value.
I had a quick question about the project. So I was looking to do non-convex optimization. So I was going to use stochastic gradient length and dynamics. I didn't know if we would cover that in class, or if that's okay if I use it.
Yeah, you can do that. I'm going to cover that.
Okay. Okay, thank you. Sure.
Professor, me and Yuji wanted to do the project together. Is that possible, or is it like individual?
For project, you have to do your individual work.
Right. So we were thinking we are both in a natural language processing class. So for that, we were moving on for a project. So we were wondering if we could use. So the idea was to use like a natural language processing model and optimize it. So we were wondering if we could use the same model but use different optimization techniques for like different projects. So I was wondering if that's allowed.
What's the difference between the two projects?
So the difference would be we would use different optimization techniques to. So the idea of the project is the same. Is that we're going to be using different optimization techniques to compare accuracy and complexities. Is that different enough for us to do, or is it too similar?
So the only difference is just the algorithm,
Right.
but the setup, the data side will be the
The
same.
data and the models would be the same. Yeah. So that.
How many algorithms are going to implement?
We haven't thought out the specifics yet, but we're just asking for permission if that's okay to do, or is that?
If you have enough number of algorithms to implement, I think that's okay. But if you, for example, if you just implement one algorithm, then easier.
More than three, maybe.
That should be fine. But you can use the same problem, but for the report you have to write your own
Of course.
report. It has to be different.
Yeah. Because
Okay.
we are in the same class in natural language processing, so that in that course, I mean.
Right. But so let's consider that if we are not able to do 3 algorithms, then I might do something different, like I was proposing for the midterm example.
Okay.
But okay, then we'll think about it.
Yeah.
You have to do enough number of algorithms, otherwise it will be too similar.
Right.
Yeah.
Okay.
Yeah, let's say maybe at least 3. Each of you do 3 different algorithms.
Okay.
I've already done something in my computer, but I think it's another language. Maybe. Oh yeah.
Okay. Well, if you want to show me, you can come to the office hour.
Oh, of course. Yeah.
Yeah, so I was thinking about the Reddit data set, right? So apart from sentiment and also one other thing, I got your email, but I didn't get the go actually.
The group project.
And if he does not, then it's fine. I can do the other project that I was interested in doing. So that's completely fine. You can focus your project on both this, but I can just separate. Oh, also another thing. I did not get your. It only has the text. It doesn't actually have the.
Attached by the email. I don't
Right.
know why.
You can just resend me the email.
Okay.